Very much. Good morning. My name is Bozorgnia. This is the first session. First, I want to congratulate Pierre became 21 years old, so it means legally we can drink here. This session is related to the ground motion, earthquake ground motion, as well as tsunami characterizations. There are 3 presentations here, each of them about 25 minutes. That was the plan. Originally it was 30 minutes. Now we reduced it to 25 minutes. So we try to finish each of presentation for 25 minutes or so. So the first, I'm going to talk about NGA and so on that Professor Musallam also mentioned. Then Professor John Stewart from UCLA is going to talk about NGL liquefaction. And then Professor Pat Linné from USC will talk about tsunami engineering. So these are 3 very different topics, 3 very different research projects, but the common features of these 3 projects are these. First, they are multi-researcher. There is not single researcher with $20,000 and publishing a couple of papers. These are different. There are multi-researchers, multi-university. It's not only one university, several universities are involved in each of these. Multi-funding agencies. These days, large projects are very hard to have one funding agency to fund everything, so we have to put various funding agencies to collaborate. In terms of contractual issues is really challenging because each of them, they have different terms and conditions, but that's the way it works. And then all these projects are multi-year. It's not just 6 months or 1 year, multi-year. So it's really like solving a complicated puzzle one by one. It's a combination of academic researchers and practitioners. This is what we are really proud of it in the last 20 years. If we want to do something important with a real impact, we have to collaborate among different universities, and we have to collaborate with practitioners, not something abstract. So it's painful, believe it. I know what I'm talking about. It's really painful for technical management of these things. I've not slept many nights on various projects. Researchers in University X doesn't reply. Practitioners from another company doesn't reply. But bringing together all these things, really the impact is enormous, When we started many of these projects many years ago, we never thought that the impact is a little bit painful in terms of management, but at the end, the impact is enormous nationally and internationally. And these 3 projects that you will see have all these things in common. So NGA East, you see, I have Christine Goulet first and my name second. I have always said my biggest contribution of NGA East was to convince Christine to join the project. The rest was history, and she has been doing a world-class job. Is basically Central Eastern US. And like anything else, we were working on NGA West and other projects, and a colleague from Nuclear Regulatory Commission came several years ago, and I told that person, we are interested in subduction. But that person said, there's no nuclear plant in Pacific Northwest. I said, what about East? Then the rest is history. So the Nuclear Regulatory Commission funded this. This has been the largest projects in the last 20 years of Pierre, in terms of number of researchers, in terms of budget and so on. Like any other projects that we have been doing in NGA, we create large databases, simulated ground motion database, empirical ground motion database. The database are public. We are very proud of it. This is not just that, trust me, and my database is better than yours. It's public. You can check and you can find errors, and it happens all the time. And as Professor Musallam mentioned, one example is that in the last 12 months, more than 1 million downloads of NGA West 2 database happened. is really popular, and we get demand from all over the world about it. Highly collaborative, this is another feature of all these projects. They are highly collaborative, not that I work in my cubicle and I write a paper and I win Nobel Prize. That's a very good thing to do, but this is different. This is real, these are community-based projects with highly collaboration among the researchers, graduate students, postdocs, undergraduate students, and as the result of these projects are not going to be seriously challenged, because already the challenge and fighting, not physical fighting, intellectual fightings happen in the meeting after meeting after meeting over 2, 3, 4 years, and then the impact is enormous. So in NGA East, 55 people worked. And you can imagine how much time it is to coordinate this thing, Christine and I, on that. But we are very proud of it. 55 people in academia, in practice, in NGA West, 32 people work. And the paper that we wrote in NGA West really has 32 authors. And again, everyone should get credit. So for NGA East, the brave funding agency originally was Nuclear Regulatory Commission. They came, and original always in the multiple funding agencies. The first agency is very important because it creates the chain reaction. Then we got funding from Department of Energy, Electric Power Research Institute, practitioners, utilities, and USGS intellectually. So these are the sponsors of the project. You see the challenge that we have. This in the left is the ground motion database that we have for the West. Obviously lots of data is a magnitude versus distance, and in the right is the ground motion, the empirical ground motion that we have in the central eastern US, east of Colorado. The seismicity is very different, but there are 100 nuclear power plants east of Colorado. There are 200 million people living. So the impact is enormous. So we don't have so much data. So it's really challenging. So it means that we have to heavily rely on simulation of the ground motion. And various simulations happen by different groups. And the challenge was really how to extrapolate the ground motion for central eastern US for large magnitude once we don't have empirical data. So simulation helped, and lots of other technical issues that various working groups worked. Again, we solve this very complicated issue by having multiple working groups, multidisciplinary effort, multiple institutions, and interactions with end user and utilities. So you don't have to read these things. These are the working groups and the way they interacted. It was really challenging to manage that one, but it worked well. So the process which has been taking over the last few years, I'm summarizing it in one slide. Basically, we asked the community inside the NGA East and outside NGA East, anyone in the US, to make model. 18 models were developed by the community, not by a couple of individuals, by different teams. And then these models, they had not the common magnitude, distance, range, and so on. So the NGA East team basically harmonized all these models, and seed models were developed. And then for the very revolutionary thing, it happened also in another project in the western US for Diablo Canyon nuclear power plant, and we followed that one. So instead of using 18 models, if you remember from your linear algebra, if you have the eigenvectors, you can generate the entire space. Similar concept. It's different, but similar concept. With the 18 models, we developed thousands of models, not the data points, thousands of models generated. And obviously, in practice, we cannot use thousands of models and so on. So we rediscretize it and bring down the final models to 17 models, but with uniformly distributed all over, with assigning weights to each model. Visualization was very important, and we had extremely talented postdoctoral fellow, Nico Cohen, is sitting back there, and he has been working day and night on these things. Instead of working on all these curves, which are still important and we use it for visualization, we use a new technology which is Salmon's map. Basically, all these models are mapped in many dimensions into 2 dimensions, and the distance between 2 models, it means if they are resulting close or differently. That was very powerful tool of the visualization. So the summary of the project is that 17 median models out of 18, 10,000, and coming back to 17 have been developed, including various standard deviation models, single station, sigma, ergodic, and so on, developed. Many reports already established and printed online. You can download them, all free of charge, obviously. And the project has been under SHAC umbrella. If you are familiar with in the nuclear industry, the review process is very formal. It's not just 2-3 reviewers and come and chat and you incorporate. It's not even like reviewing of papers in publications. There is a panel of participating peer reviewer panels. Participating, it means during the life of the project. They all give you comments through life of the project, and formally they'll write you comments, not 1, not 2. We got 700 comments from them, and the team went through all 700 comments, incorporated their comments. The report went back to the reviewers, and we are waiting for the second round, and we had a conference call. We are hoping to finish and finalize and publish the peer report by mid-2018. When I say report, it's going to be thousands of pages, literally 600-700 pages of the original text of the report, plus thousands of, I know one appendix of that has about 600 figures. So it's going to be thousands of pages. Obviously, we are going to post it at peer website. So that was NGA East. Remember, several years ago, we started with NGA so-called West for active technology region, California, West Coast, Middle East, Japan, and so on. Then NGA East was initiated. NGA East has been the largest project that we have had. And then subduction, especially for us, for Pacific Northwest, is extremely important. Magnitude 9 happened 300 years ago. It will happen again. It's very different than others. And especially, I wanted to write all the names. Again, this is our really our feature and our strength. There are 30 people involved, but I wanted especially thank Tadahiro Kishida. He was a postdoc with us. Now he's a faculty member overseas. And Dr. Silvia Mazzoni, she's here. She has been working day and night, weekend. I met Silvia over weekends in Walnut Creek to go over all these things. Extremely dedication. I'm so really proud of our community. It's unbelievably dedication of the researchers and practitioners. I have to open this parenthesis. We don't pay anything to the practitioners, but they come to our meetings because it's important definitely for them and it's important for us. So the contribution is not really transactional that we give you money, then you come to our meeting. It's not really like that. It's amazingly intellectually rewarding. So NGA-Subduction. So we talk about subduction. This is a cartoon that you know subduction earthquakes are different. One slab is going below the other slab, and 2 types of earthquakes. I teach in my course this thing. So there are 2 types of earthquakes happening in the subduction, and we both call them subduction earthquake. One is happening at the interface, one slab versus another slab interface, and usually large magnitude can happen. Magnitude 9 in Pacific Northwest happen, Tohoku in Japan magnitude 100 happen, and tsunami can follow up after that. The other type is within the slab, usually deep, 50, 60, 100, sometimes in the Colombia, 200 kilometers deep. It's within the slab, and we call it a slab event, in a slab event. Still, we call them subduction. They are different. And under NGA-Subduction, we collect data for all of these. This is the largest database that we have had. It's enormously. There are about 210,000 records. One by one, these records have been processed and signal processing. I joke with my electrical engineering colleagues that we do signal processing more than electrical engineers they do, because we have to remove noises, high frequency noise, short, long period noise, and so on. All 210,000, one by one, we put it under microscope with interns, graduate students, postdocs, people with 30 years of the experience, and the database is forming is what, 1,800 events worldwide. This is worldwide. All of the database that we have is worldwide, magnitude 4 to 9, and we have, as I mentioned, SLAB interface as well as SLAB. So the database, the way that we have had it for the other NGA is that response spectra from 0.01 second all the way to 10 seconds. We, for 11 damping ratios and lots of activities ongoing on that one, we are pushing envelope, and we are computing, and we are releasing Fourier amplitude spectra for all of this. The community in the ground motion hazard, more and more they are convinced that we should go through Fourier amplitude spectra, make a model, but come back to response spectrum, because I know engineers, structural geotechnical engineers are interested in response spectra. We are not going to drop response spectra, but I think we should go through different route is more reliable. So duration, obviously, we are taking care, because magnitude 9 duration obviously is much longer, and that's another important. The database includes motions from 1970s, the analog recording, and we borrowed from literally large tapes. They sent us from Washington, state of Washington, large tape. We sent it to San Jose to read large tapes and analog, but we have all the old data, and obviously we are now collecting lots of new digital data. The latest events that we have, 2010, very important event in Chile. We signed MOU, Memorandum of Understanding, with colleagues in Chile, Japan, and others. If there is an earthquake, it's important earthquake, I personally write memo and I visit the facilities. We need to collect them. We just cannot close our eyes. And obviously we were thinking that we have the greatest database on the face of the earth. Suddenly a few months ago, two earthquakes in Mexico happened, and the largest in a slab event that we had before the Mexico earthquake was 7.8 magnitude. Suddenly 8.1 happened. So again, we cannot close our eyes. We are collecting the data as we speak. We signed MOU with various colleagues in Mexico to release the data, at least for the research. The database includes everything that previous large projects had. So this figure shows magnitude versus distance, and the largest and most reliable earthquake ground motion model for subduction has been project BC Hydro project. That's called BC Hydro model and the database. As you see, our database is much larger than BC Hydro, and we made sure that we are not missing any other data. So this is more or less the same figure, magnitude versus distance. You see the largest magnitude that you have, 9.1, is from 2011 Tohoku earthquake. Professor Steve Main and I were in Japan on Wednesday, and the magnitude 7.2 happened, and we flew back. Friday, magnitude 9 happened with tsunami follow-up, you have seen it. And then obviously we important event in Chile, and we are collecting Alaska data from Alaska. Taiwan is very important. We are working, again, we signed MOU with Taiwanese colleague. They are going to give us, they gave us all of the data that they have, and obviously for us, Pacific Northwest. Fortunately and unfortunately, Pacific Northwest, we don't have recorded ground motion, especially for magnitude 9 interface. So we have to rely on other data. It has been very challenging. Is it a really good assumption? We have spent days on that, tens of hours of conference call. What should we do? For the US Pacific Northwest is extremely important. Should we rely on the other data? Should we adjust the other data for Pacific Northwest? We don't have data in magnitude 9 recorded motion. And in fact, the decision is that about 35 of us in the entire community who are working on this, we are going to write a white paper specifically on Pacific Northwest, why we are doing it, and what else we should do in the future. Collectively, we are going to write, because it's very important, it's going to impact tremendous facilities in Pacific Northwest for insurance industry and others. So you see the database is huge, and you see all over the world is international. Always, unfortunately or fortunately, we don't have so many data in the US that we rely only on the US data. We have to rely on international data. The largest number of this on the left is the records, number of the records, and in the right is the number of events. The largest number of events, earthquakes, that we have is coming from Latin America. The largest number of recordings is coming obviously from Japan and then Taiwan. Any earthquake in Japan, we get between 500 to 2,000 recordings. 500 is official, 2,000 private industry, and again, signing MOU will get it. Duration, obviously, you're familiar, is subduction, large magnitude. Duration is, the top one is the duration, Arias intensity. Professor Musallam mentioned also, is that you see the duration of that comparing to 1989 Loma Prieta that we had it next door. And this is the Chile earthquake. Obviously, duration for this subduction earthquakes are very important. Status of NGA-Subduction, the database is complete. We went through tremendous amount of the pain and the error finding and so on. Database is messy process, but is essential process. It's like investment. You spend lots of time and effort intellectually on the database, but once you have it, it's so intellectually rewarding that you can do lots of good stuff out of it. The database is almost continuous. Still conference call today and tomorrow between the postdocs and others. They are finding a bunch of errors. Different teams are working on the data. I have to mention these things. I have only one more slide. The development of these large databases is very different than what we used to do 20, 30 years ago. 20, 30 years ago, myself, I had a database of like 500 data points, and I never shared it with everyone because I spent so much day and night on that. We passed that era. So the database is community database. It's not developed only by the database working group. Database working group develops the database, but lots of modelers are checking it continuously during the life of the project. It's not that you have a database and we pass it to different group. It comes through interactions, because modelers, they check the data and said, something is wrong with that. Go back and check. They go back and check, either they confirm it or they revise it. It goes back and forth hundreds of times, not once or twice, over 3-4 years. So developers are, model developers are working on that one, ground motion simulations for, because we don't have enough data have been done by the interaction with the UC Santa Barbara's seismologists. Plan is to finish the project by early mid-2018. I had it last night only early. I had dash mid that if you're behind, you guys don't complain. So in the future, very near future, already done. This is 210,000 time series, and we have been requested by the engineering community that they don't want to wait for a couple of years that we release everything. So in the next literally few weeks, we are going to release at least 500 databases that we believe are the most important data that for the community, especially engineering practicing community. So those will be released very soon. Concluding remarks. I'm not going to have summary to repeat myself. So these are all NGA projects. Really, as I mentioned, they are multi-year, multidisciplinary, multi-campus practitioners involved. They are community-based project, not individual project. And that is the strength of these things. As a result, the impact is enormous. Professor Musalla mentioned, when we published these things in 2008, we never thought that over 10 years or 9 years, we get 1,000 citation. It was not even imaginable for us, but the impact is enormous. Interactions is absolutely the largest, more powerful intellectually people on the face of the earth. They enter to our rooms and they believe that their models and the data are great. After they leave, they told us that after they leave, oh, we learned something. So interaction between different groups, all of us, we learn, and as a result, the quality goes up. Thank you very much. I appreciate that. And if you have a couple of very quick questions, I can answer. Otherwise, we go to liquefaction. Any quick question? Everything is clear. So we can have drink, 21 years. All right, thank you very much. So the next speaker is Professor John Stewart from UCLA. He's talking about NGL. Now we want to copyright the NG, next generation. Instead of ground motion is liquefaction, and Professor Stewart is going to give an overview.
Then we need to find the PowerPoint. Let's see, do you know where it is here? Oh, here it is. This is it. This is it, yeah. Okay. All right, good morning. I know we've had, probably there's a need for some bathroom breaks out there, so feel free to sneak out the back. It's been a long session. I'm going to be talking about liquefaction, as Yusuf mentioned. This is the Next Generation Liquefaction Project, and I think as I go through it, you'll see that it's in many ways inspired by and modeling the Next Generation Attenuation projects that have gone on in Pier. There are 3 PIs essentially managing a very large project: Yusuf, Bozorgnia, Steve Kramer, and myself. There's a lot of students here, I understand, so just to make sure that we all understand what it is this project's dealing with, it's liquefaction. Liquefaction basically is a significant loss of shear strength in soil due to a pore pressure increase. And when you get the pore pressure increase, the water needs to go somewhere, and it will often flow up to the surface, forming boils like we see here. We know that when liquefaction happens, it can destabilize a lot of critical infrastructure, like levees, dams, slopes, and the like. The picture here is the Lower San Fernando Dam. It can also rupture critical infrastructure like pipelines. This is an area affected by the Northridge earthquake with both ruptured water and gas lines. And of course, as liquefaction occurs, the ground softens, displacements occur, that will affect overlying structures. So this is a picture from 1906, but there's countless examples of this up until the present, all over the world. Liquefaction, of course, is not a foreign concept in California. It's been recognized as a serious driver of risk and hazard. And as of 1990, so quite some time ago now, there's actually state law that requires that developments over a certain size consider liquefaction as part of the planning and engineering process. So the NGL project is what I'll be talking about. It is a community project, much like what Yusuf Bozorgnia was just describing. It really had its origins here in the Peer Center, although Peer Center folks working very collaboratively with people all over the world, particularly New Zealand and Japan. Much like with the NGA projects, really the intent here is to develop new models that will really transform the field and represent a new benchmark that we'll move forward from in terms of modeling these effects. What I'll try to cover today is very briefly why we were motivated to undertake this effort. Goes back a couple of years. I'll talk about how the project is structured and organized and what is the status of the work. So just very briefly, the subject of liquefaction and how we deal with it, you can basically think of three major components in it. There's susceptibility, triggering, and effects. Susceptibility is essentially looking at a particular soil material and deciding whether it could potentially liquefy were an earthquake strong enough in size to occur at that site. So for example, clean sands are susceptible, clays are not. And it gets more complicated than that as you go through the details, but that's the basic concept with susceptibility. If you find that a material is susceptible, the next step is to look at triggering, which is basically to say, for susceptible materials in a given amount of shaking, would you expect the pore pressure increase and the strength loss to occur? And then the third one is, if you do expect triggering, what kind of effects would you expect in terms of deformations, instabilities, and the like? So all of these are parts of liquefaction modeling, liquefaction engineering, and all three of them rely to a great extent on data. We use empirical observations from past earthquakes to guide the model development. Now, Yusuf was describing data sets that are getting pretty big, tens of thousands or maybe even over 100,000 data points in some cases, okay? We're talking about a totally different scale here with liquefaction. The data sets are small. Some of the recently published, say in the last 10 years or so, triggering models are relying on a few hundred data points. Some of the effects models are relying on a few dozen data points. So it's really a different order of magnitude of the amount of data. And with small data sets, individual points are very impactful. And this is a figure from a paper by Idriss and Boulanger a few years ago that shows, in this case, about a dozen data points really having a tangible impact on how a triggering curve is being drawn in this case. And those differences end up being quite impactful in engineering practice. Another issue that we face currently in liquefaction problems is that the data sets we have are incomplete. This is actually true with ground motion too, but in the case of liquefaction, if you look at the figure on the right, the symbols there indicate case histories that are in current models, and there's a lot of points there, but there's some appreciable gaps. There's nothing below about 12 meters, very little below about 10 meters depth. There's good reasons for that. There's very little above about a magnitude 7.6 or below about a magnitude 6. These are important ranges for a lot of applications, and several other examples there. So there's some pretty big gaps in the data that we're building our models from. So we have models for all of those effects I described, susceptibility, triggering, and effects, but they provide different outcomes. One way to look at it in a very schematic way, if we look at CSR, which is cyclic stress ratio, a measure of the shaking intensity, versus the penetration resistance, with the dots representing ground failure or liquefaction and the open circles being no ground failure, one could draw different curves through that data set and come up with different models, and it's pretty easy to understand how that could be. But it's actually more complicated than that schematic depicts. And the differences between the models come from a variety of reasons. In fact, the current models are based on different data sets for different modeling groups. Those different modeling groups interpret the data that's plotted in these sorts of plots in different ways. The models necessarily need to be extrapolated beyond the data range for reasons I've described. That's done in different ways by different modeling groups. And with small groups working more or less independently, there's the potential for errors in the interpretation of the data. All of these things are a result of the previous paradigm for how research on projects like this have happened, which is essentially professors and students or small groups of investigators working more or less independently. The whole NGA and now NGL framework is trying to develop a new way of developing these models and looking at the data that's more collaborative. Recognizing the problems in the liquefaction community with the use of these models, the National Research Council formed a liquefaction committee. It was formed in response to really a community request for guidance. It was a multi-year assessment of the state of the art in practice in liquefaction that ended at the beginning of last year when they published their report. The first recommendation in that report was to develop a public database of liquefaction case histories that everybody could access in the development of new models. There were a number of other recommendations, and I won't go through all of them, but just to list two, the concept of having models that are inherently unbiased and with a definition of what the uncertainties are in the use of the models was recommended for all of these aspects of the analysis that I've described. And there's also a recommendation that when we extrapolate beyond the data, which is necessary for the reasons I've listed briefly, that needs to be done in a way that is really rooted in the physics of the problem. So NGL is really trying to respond to that. Of course, NGL started before that NRC report came out, but we were sort of thinking the same thing. NGL has a structure which is essentially starting with a field case history database. We recognize that even though the database can improve on what we have now, there will still be ranges of the parameter space that won't be sampled, so we're going to need supporting studies to support that. And then we need to develop models, and as the model development goes on, there's various teams doing it. They're sharing common resources, and they have to produce models that cover a required parameter space for practical application. So I'll try to very briefly talk about each one of these three components. The database is a formal SQL relational database that's accessed through a GIS interface. It covers liquefaction, ground failure, and non-ground failure cases. And a lot of our efforts over the past year and a half or so have been in creating this rather sophisticated database and GIS interface structure. You can see a screenshot of the map with various locations where data is currently populated. Our efforts so far hasn't really been in massively uploading data into it, but creating the architecture and having that go through extensive community review. But there are actually 63 sites with about 350 case histories in there presently. Within the database, the formal structure is that there is information on site in one group, basically, on the events, where we basically borrow from NGA, and on field performance, which comes from field reconnaissance. This information is all linked through something called a database schema, which is really the skeleton, the underpinnings of the relational database. We've developed mapping tools and plotting tools so that you can access the data, visualize what's going on, and use it. This has not just been done, as Yusuf was describing, with a postdoc and a professor. It's undergone pretty extensive community review. People all over the world have used it and provided their input, and the product has been improved as a result of all of that. And this is being managed by a database working group chaired by Scott Brandenburg. And then you see the other members there, Ander Chetan, Kevin Franke, Rob Moss, and then the postdoc, now research engineer supporting this activity is Paolo Zimro. Supporting studies, just briefly, the need for it, as I've mentioned before, is the models have to work beyond where the data exists. So the data space is a little too narrow. So we want to use supporting studies to guide the extrapolation of models out over the space where we need the models to work. That could be laboratory studies, could be centrifuge modeling, could be simulations, depending on what kind of problem it is we're dealing with. We've done a little bit of this. The funding levels haven't really been enough at this point to do massive levels of supporting studies, but we have done some scoping studies to essentially define what we need to do in a few critical areas, including aging and best practices on selecting of the critical layer, which is the detail in building these models. With the model development, this is a phase that hasn't started yet. We need to get the database and the supporting studies a little further along, but that will happen before too long. That will at least form the team so they can start interacting with the database developers. We anticipate that there'll be an open call. Anybody who wants can participate as a modeler, but there will be certain requirements. They have to agree to attend meetings, share their results, and have some kind of coordination of publication. We don't want some cowboy going off and publishing before everybody else. The models, as I've referenced several times, you can't just have the model work where it feels good, where you know you have good data. It has to work where the engineers need it to work, so there needs to be functionality over parameter space and defined uncertainties in all of these models. And all the different things I've talked about need to be captured in the broader project. Not every modeling team needs to do everything, but broadly across the whole project, we need to cover susceptibility triggering and a number of effects. What effects exactly are in there is evolving. Sponsors have different interests, but what I've listed here are kind of the minimums. The organization of the projects on this slide, if you kind of start in the middle, that's essentially the PI group that manages the project. They're advised by wise persons that comprise an advisory board. And then if we move up from the Project Management Committee or PMC, you've got the Joint Management Committee. That's essentially sponsors who are providing input into how resources are allocated in the project. The bottom row there are the three major phases of work on data, supporting studies, and model development, and it's the database group which is actively working now. Status, one of the big tasks, frankly, for me and others, thank you, has been trying to round up funding for all of this. This is not cheap. And so we're talking to lots and lots of groups. We have some funding currently active, and we hope that will be ramping up considerably in 2018. 2018 and 2017 as well, really, are pivotal years in this project. We're going from a small, largely volunteer effort to something more substantial, where we really want to get this thing moving in a pretty aggressive way. So engagement with funding agencies has occupied a lot of my time. The database is mainly what we've been focusing on. The structure is now in place. We had a major review in July of last year here at UC Berkeley, where we got some good input. That's all been accounted for. The model's been revised, the data model. The model's on UCLA servers now. It's being moved over to DesignSafe, or at least mirrored there. And the working group managing this is now operational. We have had some supporting studies, as I've mentioned. This is an area that we really need to ramp up our activities. Let me just acknowledge the sponsors of the project. Really, none of this would have been possible without PEER, and PEER's support of this really came from Caltrans. So Caltrans and PEER provided the seed funding that really got this effort going, both in terms of direct support and supporting of workshops. Last year, near the end of the year, the U.S. Nuclear Regulatory Commission provided funding through the Southwest Research Institute in Texas, and so that is now in place. And the Department of the Department of Interior Bureau of Reclamation has recently agreed to start providing funding for the project. So this and a number of other agencies will be coming on board, we think, next year. And so we're very excited about NGL. We think it's going to make a difference. And thank you for paying attention to my talk.
Questions for Professor Seward on next generation liquefaction? The database, already people can log in and download whatever you have.
They have to establish an account and then they can do it.
Okay. Any other questions, comments? Thank you very much, John. I appreciate that. So the next presentation, again, as you see, is similar in concept, totally different topic as what we are doing. 5 western states, the state of California, Oregon, Washington, Alaska, and Hawaii. put together pooled fund animation characteristics of these large projects, multi-agency. They put pooled fund for really designing and analyzing structures, especially bridges, for tsunami. And the leader of that is multi-university organizations involved and so on. The leader of that project is Professor Pat from University of Southern California. Welcome, Pat.
All right, thank you, Yusuf. Yeah, my name is Pat Lynette. It's a pleasure to be here and chat about tsunamis this morning. So what I want to talk about is a project that's been led by Pierre, whose goal is to put together a guide spec for tsunami loads on bridges. So a little bit of foreshadowing, some pictures of failed bridges from Japan. So the motivation for this project was what we saw when we went out and we saw these failed bridges in Japan. And we recognized that similar things could happen throughout the west coast of the United States. So it's kind of a similar type of thing that happened in the Gulf Coast after Katrina, where lots of damage happened, lots of failures to bridges happened, and it motivated the AASHTO guideline for bridge design for hurricane waves. The same type of thing is now ongoing on the west coast of the US, and we'll talk about it now. So overall goals here. So the project objectives center on the development of a design guide spec for the estimation of tsunami loads on coastal bridges. The work will include verification of the guidelines by model testing and comparisons to calibrate the equations. We're going to use a lot of numerical modeling in here. We're going to rely on that to fill our gaps when we talk about all the design parameter space that you might have in a bridge. We're about 2 years into a 3-year project, so we're getting towards it. The final product here will be a guide spec, so a relatively short document with a commentary talking about how you estimate the loads from the hazard and how you do the detailing. We'll talk more about that as I go on. As Yusuf said, this is a pooled fund project, primarily through the state DOTs on the West Coast. 5 major pieces, and I'll go through these and I'll talk about some of the details. So the first 2 groups are the main pieces. The first group is working group 1, that is to estimate the hazard. Okay, so we have to build a database of tsunami hazard, and we have to find a way to take the information from that database and estimate the site-specific local hydrodynamic properties where the bridge is. So that's primarily Honky Theo and myself. So Honky's role here, you may have seen his other talks. He's bringing in the probabilistic hazard onshore, and then my responsibility is going to take his results and figure out how to get a site-specific local hydrodynamic characterization. Working group 2, the equations, the load, how to calculate the forces given the hazard. That's Michael Scott primarily. Ian Buckle, hopefully we're bringing into the group soon, and also Tom Murphy is a part of that from Modesky and Masters. I'll say there are many other people in this group who are working on this project. I'm only listing right now the primary leaders, the people who are getting money, essentially. Groups 3 and 4 are minor pieces of this project, relatively minor pieces of this project, and group 5, led by Tom Murphy, who put together the actual words, the spec. All right, so let's get through it. So I'm not sure how well we can see it. I think you can see it all right. This is our outline, right? So this is what we're working towards. Does this have a pointer? Yeah, that has a pointer, right? So primary pieces, not strong enough. Primary pieces, group 4, is the hazard, okay? I'm gonna go talk a little bit more about this as we go on. 2 different levels. There's a coarse, simple, hopefully conservative level 1, and then there's a level 2 hazard assessment where you do sort of the full suite, the best that we think we can do right now. That goes into the loads where we talk about horizontal and vertical on the sub and the superstructure, bring in buoyancy when we talk about vertical. Overturning moments, dynamic loads, so we're now talking about the distribution of the loads and the time response. And then the last few sections are detailing, addressing scour, and addressing debris. All right, so that first piece, the hazard. So 3 main pieces. First main piece is the database. Okay, so we need a database of tsunami hazard. This is Honky's piece. And so what he is doing is he is giving the probabilistic hazard and we're propagating it onshore. So this is quite a challenge. We need a complete hydrodynamic assessment, an inundation line essentially from San Diego through the Puget Sound along the west coast, and then all of Alaska and Hawaii. Okay, so there's a lot of data, there's a lot of information that goes into this. The entire coastline has to be covered to some degree. These maps are at the 1,000-year hazard level, which was a bit of a challenge for us. So maybe some of you are familiar with the new Chapter 6 in AAC 7, AAC 716. So we have a tsunami loads chapter in AAC 7, but it's using the 2475 hazard level. Okay, so all of that work that went into the geodatabase for AAC 7, and maybe some of you guys have gone to the website, it works pretty well. You click on a spot, it gives you hydrodynamic hazard and run up. Can't use any of that for bridges, okay, because we're at a different hazard level. So good parts and bad parts about that. The bad part is that we have to regenerate this database now at the 1,000-year level, which we are working towards. We're getting there. I'll show you where we are right now. We have variable resolution in these maps, from 10 to 60 meter resolution. So when you think about tsunami modeling, you really want 10 meters or smaller. But you can't cover the entire west coast, Alaska and Hawaii with 10 meter resolution. We just can't do that right now. So there are gaps. Between the 10 meter, you fill those in with 60. And I'll talk about the differences and what that means in terms of the modeling. We try to do some quantification of onshore uncertainties, quite challenging. And then finally, the specification of local hydrodynamic properties at the bridge. How do we do it? Okay, so there are going to be two methods. One is what we call this level 1, primarily a transect tool. Okay, so tsunami propagation is too horizontal dimensional. It's going to interact with hills and it's going to go through valleys. It's going to go through river channels. This level 1 analysis forgets all that. Okay, we're going to specify a transect and we're going to use a simple hydrodynamic equation along that transect. I'll talk about it. What you want is level 2. That's the detailed hydrodynamic analysis. You can't always do that, but when you can, you should. Okay, so here's our inundation map coverage so far. California, Oregon, Washington, and Hawaii. We're steadily getting this together. As Yusuf had said, it takes a lot of time. We've been working on this now for pretty much since the start of the project. There's a lot of work that goes into that. It's not just running models. It's running models, looking at the results, saying that's not good. Why is it not good? It's because the bathymetry is bad. Fix the bathymetry, do it again, rinse and repeat, and you have to do that throughout the entire length, California, up to Washington. In Alaska, we kind of skip over things. There's not a whole lot of people in Alaska, so we don't look at it quite as closely. Sorry, Alaska. But it's this sort of approach. It's a lot of work. We're on our way there. What these maps look like for an individual location. So this is an example of what a 10-meter result might look like. You have the red line, which is the shoreline, as it is normally at high tide. The black line, you see, that's the inundated area. Okay, so this is an example output. Wherever you see that flooded area at a given point, you have maximum flow elevation, you have maximum speed, you have direction of that maximum speed, and you have something called momentum flux, which is an important parameter when we talk about fluid drag on a structure. For the numerical grids in the database that are 10 meters, that is your level 2 analysis, right? So the database includes the hazard. The engineer doesn't have to do anything else. Just clicks on the point. If it's a 10-meter result, you have that level 2 analysis, and you're done. Quickly go over the uncertainties. We did quite a bit of study to look at modeling uncertainty, looking at different areas, using different models, using different resolutions. Here's an example of simulations for Sendai, showing tsunami flow elevation for 2 different models for Sendai. And if you look at those 2 and you don't look too closely, they're pretty reasonable. You can try to summarize these and plot these together. So this plot over here on the left, measured inundation distance versus modeled inundation distance. You want them on that 45-degree line. There's quite a bit of scatter there. Standard deviations of errors on the order of 15 to 30%, depending on the resolution. What you find when you do this uncertainty analysis is that if you're just focused on the run-up elevation or the inundation line, errors between 10 and 30 meters, they're not that different, right? So a 60 meter, or 10 to 60 meters. So a 60-meter simulation is going to give you a pretty reasonable inundation line. But then when you look at velocities, an example of that is over on the right, the velocities don't show that same behavior. Okay, so when you want velocities out of a model, you really need to be 10 meters, 30 meters are reasonable, 60 meter velocities are terrible. Okay, and so that has implications when we talk about level 1 and level 2. And there are good hydrodynamic reasons why it's harder to get velocities than it is to get elevations, but you know, fundamentally you can think about turbulence, right? So you have strong jets and eddies moving around. The spatial variations of velocity is huge, whereas the spatial variations of the elevation of the water, not quite as big. All right, so in those areas where we don't have the high resolution modeling, we have to have this level 1 analysis. And what we rely on is this transect approach. Okay, it's a similar idea what you see in AAC7. It's essentially, you know, you have a point, you have your design point, you just connect a line from that point to the shoreline and to the run-up point. Okay, so it's a straight line that connects the shoreline to the limit of inundation and it goes through your point. Along that point, think back to your junior level fluid mechanics class. All we're doing is we're keeping track of energy. Energy equation, Bernoulli equation, we're just looking at that. We're including the effects of going upslope and the effects of bottom friction. Okay, and that's all it is. It's really that simple. It is the prescriptive option. It allows you to get site-specific hydrodynamic hazard in a simple, quick way. So there's the equation. Again, you can code it in a spreadsheet. The problem with this is that there's all sorts of assumptions that go into it, right? So I consider myself a fluid mechanician, somewhere between that and a physicist. This makes me throw up in my mouth a little bit, right? So this is rough. Okay, so you have to recognize that from the hydrodynamic point, this is really coarse. You have to put on your engineering hat and say you just need something reasonable to give site-specific hazard, and that's what this is. You know, I imagine hopefully by the time I retire, this stuff is gone, and we're all just doing detailed hydrodynamic modeling, but for right now, we can't do that, and this fills that gap. Okay, so an example of how those transect approaches work. So you see that white dot, that might be the location of the bridge. In the bridge spec, we're going to come up with 4 different transects. One is a flow pathway transect, where the engineer uses his best judgment to follow the river channel around, and then you connect that to some inundation point. And then you also have 3 straight transects, which is similar to the ASC7 approach. You just click somewhere offshore. You draw 3 transects with varying angles. You apply the energy equation across all of these transects, and it gives you a whole bunch of elevations and velocities at the site. In the bridge spec, you take the average of the top 3 so that it gives you kind of an average number of these. That's the idea. This tool is going to get folded into the peer website. This is something that Silvia Mazzoni had worked on I guess over a year ago now. It was a bit of the hurry up and wait type approach, where we needed a proof of concept that it could exist, thinking that the tsunami database work would be done, and then a year happened. So this is her prototype, which she worked really hard and she put it together. It will be here. The idea being that the user goes to the site, they put in their location, they select the hazard level, they put in other properties about bottom friction, etc. You can then go and draw your own transect profile the same way I did on that animation, and the tool does everything for you. And then it just spits out the hydrodynamic properties at your site, and then the engineer uses them in the load calculations. So this hopefully will happen, and I think this will be a very big piece of this project, because we hope to also build in the ASC 7 2475 levels, so that even structural engineers who are building a building following ASC 7, they can go to the pier site, click the location of their structure, and do the same thing. Right, so this should have quite a nice impact. Right, so I said the Transect tool is a stopgap. This is an example of what you want, right? So this is the full 2D detailed analysis. You're seeing the currents in the lower left. You're seeing elevation in the animation, in the upper right. This is Alameda, just to the south of us. So this is what you can do in modeling. It's not that hard to do that in terms of the amount of time it takes. It does still take quite a bit of expertise to set up the modeling, but you kind of get an idea of the fidelity difference between the energy grade line transect and what can be done in a reasonable amount of time. And so this isn't necessarily research. These are the types of things that can be done by engineers. It's quite a bit more detail there. All right, so if we go to working group 2. So now working group 1 has provided the hydrodynamic hazard at that level. So now what does working group 2 do? Working group 2 has to figure out what the loads are, okay? So major components in working group 2, first thing you do is a literature review, look at all the options that you have out there to calculate the loads, determine how many of them are applicable to tsunamis, and then figuring out what are the gaps. What do those equations that exist miss when we talk about tsunami loads? Lots of model testing to try to fill in those gaps, which is going to be primarily numerical. And of course, the final is to specify a loading calculation approach. Equations, right? So I throw up just some of the equations that we have looked at. So the Douglas equation and the McPherson equation. So those, Scott Douglas, University of South Alabama, Ronnie McPherson, he worked at Texas A&M with Billy Edge. Those were equations that were developed in response to the failures that we saw during Hurricane Katrina. Okay? And then you have two equations from Solomon Yim's group, and then the equation that you see in the FEMA, the FEMA P646 document for vertical evacuation structures. In all of these equations, you'll see two major groups. One is a drag group, where you see the U squared, and so you'll see that in a few of the equations. And the other is an equation which goes as H squared. Okay, so again, think of your dynamic and your hydrostatic load. One goes as H squared, or the depth squared, the other goes as U squared, which is drag. All sorts of different C's up here. They all are calculated their own way. They're all different. When you think about tsunami load, you probably want there to be both this drag load because you have a quasi-steady piece, but you also want there to be a hydrostatic quasi-impulsive load, which is from the bore. Okay, so when you think about that as a general approach, the Azkabat and Yim 2014, that's what you're thinking, right? So it includes both pieces in that general form where you have an impulsive hydrostatic piece and you have that U squared drag piece. And so that's our thinking right now. We're probably going to use that one and move forward with it and modify it to accommodate the different types of bridges that we are looking at. Okay, so what are we looking at? The numerical gap studies to provide different coefficients for that equation for different types of bridges. So what are those coefficients going to be a function of? You think about waveform. So leading order, it's going to be a bore or a breaking wave or not a breaking wave. So those two pieces will lead to different coefficients that have to be in front of the equation. The bridge geometry, when you talk about super elevation, skew, and slope. Okay, so all these different parameters have to in some way modify the coefficients that go into the load. The tsunami is not always going to hit it head on. The bridge is not always going to be simple. Orientation of the deck, the stiffness, and the dynamic response. And so we're bringing Ian Buckle and his group into this project because they just did a wonderfully large set of experiments of wave loads on bridges. And so with the data that he has from those experiments, we hope to be able to tune the numerical models and really come up with a defensible way to come up with various coefficients for different bridge characteristics. So other considerations, there will be different load cases in the spec. So for example, you look at the max speed at half the flow height or the max flow height at half the speed, right? So different, you think of a time series of the flow, you have to pick up different points for the different load combinations. And one of the things that we haven't quite finalized quite yet is the load distribution. How do you distribute this tsunami load along the bridge and then calculate the moment? So still working on that. To give you an example of the type of loads that we see based on this spec, so again, this is very preliminary, it's something that we put together, Michael Scott put together, just to give you an idea of what sort of force you're looking at. So this is an example bridge up in Oregon. The 1,000-year hazard at that location has a flow height of about 5.7 meters and a flow speed of about 2.1 meters per second. You take those parameters with this particular bridge and you put it through the different loading equations, and you're looking at horizontal loads per foot of somewhere between 1.2 to 2.1 kip per foot. Okay, so it's a fairly large load, but it's something that should be able to be handled. All right, so in conclusion, my last slide, take all that information, hazard load. Tom Murphy is going to put it into, or he's going to lead putting it into a guide spec. That is supposed to be done by September. So we are well into our draft. There's a lot that has to go into review before turning it into a final. Hope to have it done by September, and then it will be usable and public. So thank you.